Hello, everybody. I'm happy to welcome you here on my online talk. First of all, I want to thank the organizers of this conference for giving me an opportunity to deliver the talk in this forum. And I want to wish all the participants, I want to wish to organizers all the best to have a wonderful and effective scientific event. And wealth and health to everybody. Today I'll talk about the extreme structure of cones of polynomials. This is the topic which I was investigating during about a half of this year. Some of these results are already delivered somewhere before, but today I want to finalize this investigation together simultaneously with introducing the new further way of investigation on this direction. So first, the talk will be planned as follows. First, of all, I'll just to remind, we'll introduce the classical Crane-Millman theorem and all necessary definitions around it. Also, we'll talk about Klee's theorem for linear operators. Further on, I'm going to show how Crane-Millman theorem works on some classes of linear operators, non-linear operators, namely polynomials. Then I'll introduce a variant of Crane-Millman theorem for a non-bounded sets of homogeneous polynomials, where the role of extreme points is played by extreme rays. Then I'll introduce the analog of Klee's theorem. I can say something, Klee's type theorem for the important special case of cones of positive homogeneous polynomials. And to conclude my talk, I will finish with the very, very fresh result, which is analog of Klee's theorem for general homogeneous polynomials, not necessary orthogonally additive. So let me start. Oh, sorry. Let me start with some basic notions, and let me introduce the convex set. A non-empty subset C of a real vector space X is said to be convex whenever, together with any two arbitrary points X and Y from C, the interval with ends in these 2 points X and Y is entirely contained in this subset C. A convex hull of an arbitrary subset A of a real vector space X is the smallest with respect to inclusion convex set that includes A. It can be the following proposition can be easily proved. It says that the convex hull of an arbitrary A from X consists of all convex combinations of elements of A. That is the following equality holds. Here by convex combination we call the linear combination of positive elements with the unit sum. Of course, we will need the definition of an extreme point and an arbitrary point X of a convex subset C of a real vector space X is called extreme if X is not the inner point of any line segment in C. We denote by symbol XC the set of all extreme points of a convex set C, and there are several, namely 4 equivalent definitions of extreme points, and they are all collected in this theorem, and you can see them on the slide. We will not stop on this. I'll just say that in 1940, a fundamental result was obtained by two mathematicians, Crane and Meadman, according to which a compact convex subset of a Hausdorff locally convex topological vector space coincides with the convex hull of its extreme points. Here, a set C is a vector space. Here a set C in a vector space X is called compact if for every its covering by open sets one can extract a finite subcovering. By the symbol cobar, we denote the topological closure of the convex hull And locally convex topological vector space is a topological vector space whose topology is determined by a family of semi-norms. For example, a Banach space or norm space are exactly what we need, and like a counter example, quasi-Banach vector space is not locally convex. And we will need a notion of locally compactness. A subset C is called locally compact if every point of C has a compact neighborhood. Here a natural question arises: how to be in a situation when the convex set under consideration is not compact? In this situation, it turns out that it's not enough to use extreme points to describe convex set, and one has to add so-called extreme rays. Before formulating the result, let me define what extreme ray is. So, an extreme ray of C is an open half-line ρ in C such that any line segment joining two vectors or points x, y in C lies entirely on half-line ρ, provided that there is at least one inner point in x in line segment x, y lying on ρ. The Klee's theorem, which was obtained in 1958, says us that a closed convex locally compact subset C of a linear topological space which does not contain straight lines coincides with the closure of the convex hull of the union of extreme points of C and extreme rays of C. The illustration you can see here on the slide. In other words, we can say that each point of C can be approximated by the convex combination of points which are either extreme points or lie on the extreme rays. And a natural question arises: what can be said if the convex set C consists of linear operators acting into Banach spaces? More precisely, this question means the following two ideas. The first one is the existence problem, which asks under what additional conditions a convex set of linear operators with values in Banach space can be recovered from its extreme points and or extreme rays. And the recovery problem, according to which we ask, is it possible to handle the recovery problem using only convex hull and closure operations? To attack the existence problem, one can try to find a locally convex topology on the space of operators acting from X to Y, under which the appropriate convex set is compact. And by applying Crane-Millman's theorem, then we we get desired extreme points. The reason the above approach does not immediately yield the desired result is, of course, the fact that the closed convex sets of operators are compact only in very special cases. And one possibility arises if the space of operators under consideration admits a good analytical description. The interest in the description of Crane-Millman's type theorems was for operators was initiated by works of Phelps and his co-authors in 1960s. They investigated some special cases, and here on the slide I present only several manuscripts with results of this group of mathematicians. They investigated some special cases, as I said, and next let me show one typical result. It was obtained by Phelps together with Morris in 1970. Let me first formulate it, and after that I will give some explanations and all necessary definitions. So the Crane-Millman's type theorem is true for the unit ball of the space of linear operators acting from a Banach space X to the space of continuous real functions on the compact Hausdorff space K. That is, the unit ball is the pointwise norm closure of the set of its extreme points whenever K is a special compact space, namely K is totally disconnected. And this means, this term totally disconnected means that every open set contains subsets which are simultaneously closed and open and open. Of course, this is not the exact definition, but it's a kind of equivalent or almost equivalent to the direct definition. So in comparison with the classical Crane-Millman's theorem, here the operator convex set and operator convex hole are used instead of a convex set and convex hole. The definitions can be seen here on the slide, and the difference is also obvious. Next, I want to emphasize that the Crane-Millman's theorem does not immediately yield these and similar results. And the reason is the fact that, as I said before, the closed convex sets of operators are compact only in very special cases. So next 30 years, there were obtained numerous results into two directions. I'll show some of them on the slide, and the following two directions were investigated in these works and the others. First is the explicit description of extreme points of different convex sets of linear operators, and the second direction is Crane-Millman type theorems. And several results on these two directions, as I said, are listed here on the slide. And here I want to emphasize that despite of the fact that plenty results was obtained in different cases, but the most general results were obtained by Professor Kusraeva and Professor Kutateladze, and they were published in the two last listed works, manuscripts. To formulate this general result, we will need the notion of a vector lattice. Let me skip the direct definition of vector lattice and let me just say that a vector lattice is a vector space endowed with a notion of ordering. where for each pair of elements there exists a supremum and infimum. You can see the direct definition on the slide. As an example, so let me provide and say that all classical Banach spaces are also vector lattices. Vector lattices, and the ordering is introduced in the following way here. When we speak about the spaces of functions, the ordering is pointwise. The order we use the pointwise order, and when we speak about the sequence spaces, the order is coordinate-wise, introduced coordinate-wise. As the main example of a vector lattice, I suggest you to keep in mind the space of all measurable on Q functions. And during all my talk today, I'll be trying to explain all the needed notions from the general theory of vector lattices, not in general, but for an just for an arbitrary vector lattice, but just like we are working in L0 space. I'll skip several definitions which are used in vector lattices, and we'll introduce the notion of homogeneous polynomial, which will be necessary to formulate the main result. And let us consider the mapping P from acting between two vector spaces X and Y, and we call it an homogeneous polynomial or polynomial of degree n if for some multilinear operator phi the following holds. Here by delta n we denote the diagonal operator. So the polynomial which is under consideration, this notion, I mean, is represented as follows. This guy is an homogeneous polynomial. Here the multilinear operator phi is called generating, and in the case when phi is symmetric, then it is unique for this P and is called associated and is denoted by the symbol P pi with head check. Yeah. So let me continue. For better understanding what I mean by introducing this object called an homogeneous polynomial, I give an example, and let me let the target space be, as we agreed earlier, L0 space. Then we take a linear operator T from X to acting from X to L0. And we construct the new mapping by the following way. For each vector x from x, the value tx is raised into the power n, and so obtained operator p is an n-homogeneous polynomial as its associated multilinear operator can be explicitly written explicitly according to the definition which we gave before. It can be easily checked if we take all arguments equal to x, and we can see that this is what we needed. And by the way, we'll need the notation. We will denote by this symbol the space of all n-homogeneous polynomials acting from X to F, and the space of all positive, I mean the cone of all positive polynomials will be denoted by this symbol. Also, to formulate the main result, we'll need some more definitions. First is the notion of a Dedekind complete vector lattice, or how we say in Russian literature, Kantorovich space or K space. F is said to be Kantorovich or K space or Dedekind complete if and only for a given non-empty order bounded subset A of F, there exists supremum and infimum. And one more definition. An arbitrary set omega is a space of homogeneous polynomial in a space of homogeneous polynomials from acting from a vector space X to a Dedekind complete vector lattice S is said to be pointwise order bounded if the set omega X equal to this guy is order bounded in F for all X in X, and omega is called pointwise order closed or O closed if for every net pi in omega and for every polynomial p from the fact that the net pix O converges to px, it follows that p belongs to omega. Also, I need to say that what is operator convex set and operator convex whole in this case when we speak about polynomials. But as you see, these two definitions are again very similar to what we discussed before. And again, we can see that the operator convex whole operator convex whole consists of all convex combinations of elements of A. So now we are ready to formulate the main result, which is an Crane-Millman's theorem for homogeneous polynomials. According to this result, the explicit formulation, the direct formulation is on the slide, and according to this result, a pointwise order-bounded operator convex subset of the space of homogeneous polynomials acting from an arbitrary vector space to a Dedekind complete vector lattice can be recovered by the pointwise closure of the operator convex whole of extreme points of this set omega. This result was obtained in 2023 and is already published in Journal of Mathematical Analysis in 2024. And I want to emphasize here that the case when n is equal to 1, in this case, the result was proved by Professor Kutateladze and Professor Kusraeva in 1982. Also, a general form of the Cleese theorem, which we discussed earlier, was obtained by Professor Kutateladze in 1985 for linear operators. But in the article which I show you here on the slide, the polynomial version of this result is still in progress, and I hope we'll discuss it in the nearest future. But what is done even for today is the Cleese type theorem for a special class of polynomials, of homogeneous polynomials, namely for orthogonally additive polynomials, which are defined as follows. We say that a polynomial, a homogeneous polynomial acting between vector lattices E and F is orthogonally additive if it is additive on two disjoint elements of E. Here I will stop on the notion of disjoint elements, and if we again think for ourselves that E is L0 space as we decided to do, then the disjointness of two functions x and y means that their supports do not intersect. One more notion is the notion of positive polynomial. A polynomial is homogeneous polynomial is called positive if it takes positive values on positive elements. We'll use the following notation. By this symbol PO. We denote the space of all n-homogeneous orthogonally additive polynomials, and again the cone of positive orthogonally additive polynomials will be denoted by this symbol with plus. Yeah. Okay. We'll need also some definitions. We call a linear operator a lattice homomorphism if it preserves modulus, and not only modulus but all lattice operations. We call a linear operator regular if it is representable as the difference of two positive linear operators. The notations which will be in use during till the end of this talk is the set of lattice homomorphism. We denoted by this symbol, this symbol, the space of all regular functionals on E. These are real valued operators, continuous operators, and the space of regular linear operators acting from E to F will be denoted by this symbol. Okay, now we are ready to formulate the Cleese type theorem for positive homogeneous Cleese type theorem, yeah, for positive homogeneous orthogonally additive polynomials. Here we see that the third, let me start with the third, the following three conditions are equivalent. And let me start with the third equivalence condition from this theorem, which states that if the polynomial P is not orthogonally additive, then P cannot be approximated by polynomials of the following form. And the form, I'll discuss it later, but first please have a glance of this theorem. Here we see that the cone of positive orthogonally additive polynomials coincides with the pointwise order closed convex hull of the set of lattice homomorphisms raised to the power of n. The second equivalence condition is the same, but for the real valued polynomials. And the first equivalence condition says us that the cone of positive functionals is the weakly closed convex hull of the extreme race of this space. This result is also published in 2024 in Journal of Mathematical Analysis. And what I was going to do is to stay on this third condition, and to say that according to this condition, if the polynomial P is not orthogonally additive, then P cannot be approximated by polynomials of the form like sums of powers of lattice homomorphism. And indeed, in this case, this sum is an orthogonally additive polynomial, and hence the pointwise order limit of any net of such polynomials is also orthogonally additive. I forgot to say that in the case when n is equal to 1, the result was obtained by Professor Anthony Wigstad in 1981. Here is the result, and a natural question here arises. Again, a natural question. Which elementary polynomial should be taken instead of sums of powers of lattice homomorphisms to approximate an arbitrary polynomial? So this is the question. The answer is the product of powers of linear operators, which are in addition lattice homomorphisms. and I'll give the corresponding needed definition here. Given new linear operators acting from E to F, we define a new mapping Q, as you see it here on the slide. This Q is an n-homogeneous polynomial generated by Q hat of the form. Here you can see it. And it's easy to ensure that this Q hat is generating multilinear operator for a given Q. One have just again, like before, take all arguments equal to X. And now the following lemma, which I show you, says us that this class of polynomials is strictly broader than the class of powers of lattice homomorphisms. More precisely, the polynomial Q is orthogonally additive if and only if Q can be represented as the power of lattice homomorphism multiplied by some multilinear multiplicator gamma. Now the third main result deals with necessary and sufficient conditions under which the following equality holds. This one, yeah? That is the following. The cone of positive and homogeneous polynomials coincides with order closure of operator convex hull of the product of powers of lattice homomorphisms. And more precisely, the formulation of the theorem tells us that the following three conditions are equivalent. The first one of them tells us that the cone of positive functionals on a vector lattice E is weakly closed convex hull of its extreme rays. The second one tells that the same is true for the cone of real valued and homogeneous polynomials. And the third one was just announced several minutes ago, a minute ago, yeah. Half a minute ago. So this is the first result obtained in this investigation. Hope it was interesting. Thank you for attention. And if any questions, you can write to me by email. Oh, sorry, by email here. So thank you for attention once again, and all the best.